All right, 13.1 video 2. So we talked about the idea of a vector valued function and these things called space curves, which is basically what the vector value function creates. It creates a space curve and kind of how to sketch them. So we're going to go ahead and try to sketch this one. Whoops, there we go. So our vector valued function here is cosine t, sine t, t. So the idea is, let's see, our x value here is cosine t, our y value is sine t, and then our z value is just t. So we need to kind of figure out what this is doing. So if we were to start with, we'll just start with t equals 0. It probably makes the most sense. If we were to start with t equals 0, cosine of 0 is 1, so that means x value is 1. The y value is going to be 0, and the z value is 0. So if you do r of 1, you would get the vector 1, 0, 0. And because we're dealing with trig here, we're going to probably not go with like cosine of 2. We're going to go with, or something like that. We're going to go with pi halves and so on. So let's go with r of pi halves. So r of pi halves is going to be 0 for cosine, 1 for sine, and pi halves, that is a pi halves, and pi halves for z. So over here now we've got our first point, which was there, that was t equals 1. The second point is going to be what would be on the y-axis, but it does have a height of pi halves, so it's going to be up here a little bit. And then let's do a couple more. R of pi, if we do r of pi, cosine is going to be -1, sine is 0, and the height is pi. So now this point is going to be out to -1, 0, but then it's going to have a height of pi. So hopefully what you can see here is what's happening is this thing is starting to curl like this and gain height as it does. And as a matter of fact, what it's going to continue to do is loop in a continuous curl around itself, just like that, where it's going to keep getting higher and higher and higher. So it's going to end up going in this direction. I probably should have dotted the lines where it kind of goes behind itself or in front of itself or whatever, but hopefully you can see what that looks like. This is what is known as a helix. And what I want you to really pay attention to here is if we did this in 2 dimensions. So if we looked at the 2-dimensional projection, basically if you stood right on top of the z-axis and looked straight down in 2 dimensions, it's simply going to be a circle. So if all you had parametrically was x equals cosine t, y equals sine t in 2 dimensions, you're going to get a circle. So the projection into the xy plane is a circle. And that's going to be pretty common when you use cosine and sine for your x and y. The direction the circle goes may depend upon which one is x, which one is y, if you have a negative cosine, if you have a positive cosine, and so on. But one way or the other, this is going to create a circle as a projection. The reason it's a helix is because basically now it's got height to it as it starts to circle itself. Kind of looks like a slinky. I don't even know if you guys know what that is anymore, but that's kind of what that is. All right, so there is the sketch of cosine t, sine t, t. So now we want to find the curve of intersection between 2 space curves. So what you've got is you've got x squared plus y squared equals 1 and y plus z equals 2. So hopefully you should recognize these now. X squared plus y squared equals 1 is a circular cylinder. So let's actually sketch it. X squared plus y squared equals 1 is basically a circular cylinder where the it's going to be revolved around the z-axis, and it's got a radius of 1. So it's going to look something like this on the top, something like this. Not so good there. Oh, didn't mean to do that actually. Well, whatever, I'll just draw it again. Radius of 1. Okay, not horrible. Then we've got this plane, y plus z equals 2. I know it's a plane because everything is just raised to the first power. So if I wanted to actually to graph this thing, the best thing to do would probably be to solve it for z. So we get that z equals 2 minus y. Let's go ahead and sketch what that one looks like. All right, so when y is 0, z is 2. When z is 0, y is 2. So it looks like it's going to be a plane. Remember that this thing is going to vary because it's never actually going to hit the x-axis at all. So it's got a slant that looks like that, and then it looks like, trying to stay parallel here, it's going to do something like this. That's not very parallel to the y-axis. Let me try that again. And then of course it's going to come this direction as well. My drawing is not very good here. Let me try that again. I need to try and keep that parallel as much as I can to the y-axis. And then I'm going to have to do the same thing going this direction. Staying parallel to the y-axis is going to make it look more like that. Not the best, but basically, if you can kind of think of it, it's almost like a board which is kind of sitting up against the wall, slanted down. It's going to have a hollow triangle underneath of it. So what does that look like? Well, when this thing actually crosses through, so you're going to get that piece right there which crosses through this cylinder. So really, when it crosses through the cylinder, it's going to make something that looks like this. And I probably should have drawn that a little bit better, because it's going to actually go out to where x is 2. So it would hit here, it would hit here, but when it crosses through, it's actually going to look something like this. That's what the slice is going to look like as you take that board and you slice it through that cylinder. Because again, it would extend down. This is not the best drawing, but it's the best that I can do right now. And again, each single point on here is going to be created by a vector valued function of some kind. So let's start off with the fact that we knew that over here was x squared plus y squared equals 1. Well, since we know that the projection down into the xy plane is going to be circular, remember that x is the same thing as r cosine theta in polar. So we could write this as r squared cosine squared theta. That's replacing x with r cosine theta. Over here, we're going to get r squared sine squared theta equals 1. Well, we can simplify that. I can factor the r squared out, which leaves you with cosine squared plus sine squared equals 1. Of course, cosine squared plus sine squared of the same angle is 1, so you get that r squared is 1, or that the radius is 1. Okay, really probably shouldn't have taken a lot to figure that out. It was a circle, x squared plus y squared equals 1 in the two-dimensional plane, which tells you it is a circle with radius of 1. That's kind of why r is 1. So how would we actually write the curve of intersection? Well, we do know that the x value we let be r cosine of t. The y value we let be r sine of t. And we know that the height of this thing, which is created by all those red vectors, was created by the plane itself crossing through, and the plane was your z value, and the z value is 2 minus y. But I want everything in terms of t, so let's just go ahead and rewrite y as a function of t, which we already have. So it's r cosine t, r sine t, that's your y, and then 2 minus y, so it's 2 minus r sine t. Okay, this is going to be your vector valued function. Don't confuse the r on the inside, because those are the radiuses, with the r on the outside, which is just your function notation. So there you go. All right, we've got one more page here, and I know it says let's try some problems. I kind of picked these problems from your book. So this is what we're going to do. We are going to sketch. This will be number 9. We are going to sketch r of t equals t cosine 2t sine 2t. We are going to sketch, leave a little space there. We are going to sketch r of t equals t squared, t to the 4th, t to the 6th, and let's do 17. I don't want to do 19 through 24. I think those are matching. So let's do 17. And I'm going to kind of abbreviate this with, so 17 gives us 2 points. It gives us point P, 1, negative 1, 2, and point Q, 4, 1, 7. We want to write the vector valued function that's going to be created between that line segment. So we're going to say that we have a line segment between P and Q. So let's write the vector valued function. So we'll write the vector valued function created by that line segment. All right, so those are the 3 things that we'll do. All right, so let's go ahead and sketch number 9. So in this case, I've got cosine 2t, sine 2t for my y and z values this time. So t is the x value, which means that this thing is going to loop around the x-axis. It's still going to be a helix. It's just going to loop around the x-axis. So the biggest thing is figure out where you're going to start. So if we start with t equals 0, now remember, you got to plug this stuff in. T equals 0, x is 0, y is 1. And z is 0. So that's when t equals 0. If t were to equal pi halves, this is kind of the important part, because once you get the first 2, the rest of it's going to make sense. If t equals pi halves, I know x is pi halves, so it's definitely coming out in the positive direction of the x-axis. If t equals pi halves, the y value is going to be the cosine of pi, which is negative 1. And then if t equals pi halves, sine is going to be sine of pi, which is 0, so z value is 0. So it looks like, if I'm not mistaken here, pi halves is going to be up, because that would be a counterclockwise rotation. So it looks like the second point is going to be someplace out, someplace out here, and then it's going to start to rotate around the excuse me, around the x-axis like this, if I'm not mistaken. That looks right. It's got to rotate up, since that would be a pi halves for the y value. So that makes sense. Okay, so you're going to trace it, put your arrows on here so that we know the direction that this space curve is going. And that's it. I mean, that's just a really general sketch. Number 13. other than the fact that these values are going to get really big really fast. Not really hard to sketch this one. If we start at 0, pretty easy. R of 0 is 0. R of 1 is going to be at the point 1, 1, 1. So 1 this way, 1 that way, 1 that way. So 1, 1, 1. This is where the rest of it starts to get really big really fast, because now if R is, excuse me, I keep saying R, if T is 2, we're going to get 4, what is that, 1664 if I'm not mistaken, 41664. This thing's going to get really big. I can't draw that one. That's 416 way out there, 64, you know, way up there. So it's going to have a point like somewhere up there. It's going to do this. This thing is going to get really big, really, really fast, insanely fast. So that's kind of what that vector valued function would look like. Again, just a sketch, you get the general idea. All right, last one. So if the points are given to us as P and Q, we want to write a vector valued function for the line segment between P and Q. Well, we can certainly figure out what the vector between P and Q is. So let's go ahead and write the vector PQ. And that's going to be Q minus P. So it's going to be 3, 2, 5. Now, if I want to write the vector valued function, it's really just writing the equation of a line as a vector. So remember, we have to have a starting point. Our starting point was P. So that's going to be 1 plus, it's a plus, the change, which is 3t. It's linear, so we know that they're all going to be linear pieces. Starting point of -1 for the y value, plus 2t, because that's my change, that's my vector. And then a starting point of 2, and a change of 5. And there is your r of t for that specific line. All right, again, not too much for this section, a little longer even than I thought it was going to go, but you should have plenty enough to work on homework.